I've got a bunch of stuff here, and I've written down a bunch of stuff I'm going to talk about. But really, we're talking about the principal axis of inertia for three mass object. So it's an object with three masses, and I've been working on the same problem for a while. And what I did so far, I'm going to show you what I did, was to find if this is a rigid object, so these are set in place. What are the three directions that you can rotate this such that this is always true. The moment of inertia tensor times the angular velocity gives you the angular momentum. But there are three directions that you can rotate such that the angular velocity and the angular momentum are in the same direction. Okay, so let me show you how I did that. I did that two ways, but let me show you the visual way, switching over here to Python. The visual way, because I like it. And it's all about what I like, right? See, this is a little off. That's good. Okay. So this is those same three masses. And what I do is I calculate the moment of inertia tensor, and then I calculate the angular momentum based on the angular velocity. And I just rotate the angular velocity vector until I find one, a value of angular velocity that has angular momentum in the same direction. So let's run this right here, run. And then if it's in the same direction, I make it magenta so you can see these directions. So the cyan is the angular velocity, the yellow is the angular momentum, and then there's this. I put one in the z direction. I didn't find it automatically, but it had to be because they have to be perpendicular to each other. So those are the three directions over which the angular velocity and the angular momentum are the same direction. I want to show that this works. I can rotate this in those directions, and the following will happen. Okay, so let me switch back over here to the paper. If the torque on the system is zero, right? So here's my angular momentum principle. The torque is zero, then dl dt is zero. That means the angular momentum is going to be constant. So if the angular momentum and the angular velocity are in the same direction, then when this rotates, the angular velocity will stay in the same direction. Now, if they're not in the same direction, angular momentum will be constant, but the angular velocity can change. And I'm going to show you both of those cases. And so one way to deal with a rotating rigid object is to make it not rigid. And that's what I'm going to do. So I have my three masses here. What I'm going to do is connect them by springs. And that way I don't have to use the moment of inertia tensor. I can just use momentum principle. Okay. So the momentum principle says that the net force, F net, on an object is the rate of change of momentum. And if I take a short time interval, then I can assume the force is constant, I can update the momentum, and then I can update the position. So really this is my thing. Number one, calculate the force. That's L. Calculate F on each object. And now that's hard, right? Because for three objects, I have two forces on each object, and both of those forces depend on the positions of all three objects. So I need to do something there. After that, update momentum. So that's going to be, let's just say F net equals, this is P2 is P1 plus F net delta T. So that just comes straight from there. Then after that, I can update the position. Update R. So I get R2 equals R1 plus P2 over M delta T. And then I just keep doing the whole thing over and over again. So there is some work here, and I set up the program beforehand because I didn't want to make it too bad. So the first thing is how do you calculate this force? And I'm using names mass A, mass B, mass C as objects like I did before. You could make this a list or something. If you have more than three objects, it starts getting really messy. So you really want to think about doing something. But I think three is the best case where you can get interesting things to happen and is doable. And that's why I like this. Okay, so the first thing, I have positions of all these objects, right? So here's my origin. I have RA, I have RB, I have RC. So I have the positions. But I want the relative to position. I want this vector. And I'm going to actually call that, I call it up here a length, but this would be RAB. It's from A to B. Okay. and then I'll have RBC, and I'll have RCA. Those are the only three vectors I need, and I can find those just by taking the difference of these positions. How do I calculate the spring force? Well, in general, I need the unstretched length, and I'm going to set these to some unstretched length. You don't want them to have the zero length because then it'll just collapse on itself. And I have a spring constant times a stretch. The stretch is going to be the magnitude of this RAB minus the unstretched length of RAB, and then I need to multiply it by a unit vector in order to make it a vector again. And that will give me the vector force on this mass. Then I can find the vector force on this mass. It's just the opposite of that. I know there's a lot going on here, okay? And I haven't even gotten to this yet. So let's just talk about this. I'm going to pick an angular velocity vector. Once I do that, I need to find the initial velocities of all these objects. They're in different positions, right? Because if I'm going to update the momentum, I need to start with the momentum. So I can calculate that as just omega cross RA. And that's actually not RA. That's actually R with respect to the center of mass. That's the one I want. And so I'm going to find that center of mass, which I did before. And then I can find the relative positions to find their velocities. This stuff doesn't really matter where the center mass is. It's just forces and momentum. And hopefully we can get the same thing. So I'm going to start off with omega equals vector 1, 0, 0. That's not a principal axis. It should not have a constant angular velocity. And we'll see if it does indeed do cool stuff. Okay. So I started a program. Let's finish the program and see if we can get this thing to work. I left some blank stuff in there. Okay, so here is... No, this is it? No, that's my other program. Where'd I put it? This is it. Yeah, okay. So let's go over this program right here. Is it even saved? Save. Okay, it is saved. So these are just graphs. We actually don't need this right now, and it doesn't really matter. I don't even know. It's angular momentum. It'll be fun to plot. So here's the three masses. They're different mass, they're different positions, and all that stuff. But they're the same as what I had before. You'll notice here that the momentum is zero. Momentum, this one does have momentum, and that one has a zero momentum. So they are moving. Let's just run it and just see what happens, just to get it to work first. Here I calculate the unstretched position length of the springs. So RAB, no. Is that what that is? Yeah. RAB is the unstretched length. No, that's the position. That is what I said. LAB is the unstretched length between A and B. These are just the springs. You actually don't need those, but I want to show springs. I'm just calling them cylinders. Then here I put the masses in a list just so I can use my same center of mass function that I built before. And I got the center mass as a vector location called RC. Then I break it into short time steps of 0.001. L0 is, I don't even know what that L0 is. This is what happens when you do things a long time. So here's the first step. I calculate the relative positions of all the masses, RAB, RBC, RCA. Then I calculate the three of the spring forces. So my notation here is FAB is the force that A exerts on B. So if I want B on A, it'd just be the negative of that. And this is the part I left blank. Update momentum. So let's do that. Let's update the momentum. That way it can look like we're actually doing something. So I have mass A dot P is the momentum. It's going to be the momentum as A dot P plus, now I need to have two forces. It's going to be FCA, right? Because I want ends in an A. That's my notation. And then I'm going to have minus FAB, right? Because that's the A on B, but it's negative because I want to go the other way, times dt. Mass B dot P is mass B dot P plus FAB minus FBC. So I want the B ones times dt. And then mass C dot P is mass C dot P plus FBC minus FCA times dt. Now I need to update the positions of those. So I'm going to say mass A dot POS, mass A dot POS plus mass A dot P times dt divided by mass A dot M. And let's just copy this. And, oops, do it twice. Do it twice. And let's change, and all I'll do is change these to B's. B, I could type it, right? But sometimes you just want to copy, right? And do maybe this is not the most efficient way, but it's my way. And then these are C. Make sure you use the correct case. C, C, C. Okay, let's see. I think it should work. Calculate stuff. Oh, that's just for plotting. Let's just run this and see what happens. Okay, so there. That's good, right? It looks like it's rotating. Everything seems fine. Let's change it up. Now, the first thing I want to do is to make I want to make it rotate and not move. So I want the total momentum to be 0. I can do that fairly easily, which I'm going to change anyway. Mass, I'm going to put mass C. That's just the initial momentum up here. I'm going to change this one to mass C dot P. Ooh, that's not a C. C dot P equals negative mass A dot P minus mass B dot P. So now the total momentum has to be 0. So it should stay stationary. And you'll notice that they're wiggling a little bit. Okay, that's fine. That's fine. That's because it's not a real rigid object. It's a fake rigid object. Now, I do want to do. That's fine. Now I want to set the angular velocity vector. So in this case, I actually already have the angular velocity vector as in the negative. I'm in the z direction, right? That's in the z direction. But let's just do it officially, and then we'll do in the x direction, and then we'll find the principal one. So I'm going to say omega equals vector 0, 0, 1. Now, how do I? Oh, let's move this thing up here. Oh, let's do this right. That's fine. So I have the momentums. I'm going to change them before I run my thing. So after I do this, I have the center mass. Now I can say mass A dot P equals mass A dot M times the cross product of omega and R. And R is going to be R mass A dot POS minus RC. Because that's that vector from the center mass to mass A. And then I can do the same thing for mass B dot P equals mass B dot M times the cross product of omega mass B dot POS minus RC. And finally, mass C dot P is mass C dot M times the cross product of omega mass C dot POS minus RC. So this should still be rotating in the same direction, but I gave them all an initial velocity. And it should have a center mass of 0 velocity too, but let's just see. Okay. Very nice. I kind of just like looking at that, you know? Now, so in that case, the angular momentum and the angular velocity are in the same direction because the angular velocity stays constant. We know that if I put omega is 1, 0, 0, then this does not work. So 1, 0, 0. That's all I'm going to do. So it's rotating. And I guess I should plot. I can plot the angular momentum vector. That's what I'm going to do. No, that's constant. I don't want to plot the angular velocity vector either. That is, look at that. That's so cool. Let's run this for a longer time then. Let's run this for 10 seconds. So it's not rotating in the same constant way. the angular velocity vector is not constant. I hope that's clear. I mean, we could plot that. But the angular momentum is constant. I don't think I'm going to plot those because I don't want this to take forever, because I want to use the principal moments of inertia. So let's go over here, and I'm going to go back over to my program right here. Remember this one. So I'm moving it and finding principal moments of inertia, and I printed them right there. So let's print, and I did it with a moment of inertia tensor too. So let's just use this as a principal moment of inertia and see if that angular velocity works. So I'm going to go back over to here. I'm going to use this for my angular velocity, which I have up here, and let's see what happens. Okay, so it's rotating. And it's constant. Look at that. That's a constant angular velocity. You see how that's different? Oh, wait. That one moved a little bit. Okay, it's not. It's not constant because it's close. It's close to constant, but it's not. Let's see what I actually had for up here. I have, let's use these values. Oh, this doesn't like that. Okay, well, it's close. I could get the exact value, though. I don't know why that's not working. Play. Can I play that? This whole thing is locked up. Okay, don't worry about that then. Let's do another moment of inertia axis. This is the same one. Okay, you see right here, I actually printed out multiple ones because of the way I did this. Let's try this one. It's close to the same thing. I'm kind of excited that works. Let's just try this slight variation and see if this is more stable. It's not going to be perfect, but that's perfect right there. Okay, so it's starting to go off axis. So that's fine. It's not completely stable, but let's just try another moment of inertia axis. Let's try this one. We already did the Z, so now we're down here to this one. And you'll notice here that I calculate this. No, that one's completely different than that one. Let's just do this one. Copy that one. Go over here. Paste it. Run it. So it looks good so far. Now let's just see if it flips. Okay, that one's pretty good. That one's stable. So we have, and this is what you're going to find, that you can get the three principal moments of inertia axes. Two of them will be stable. The Z and this one are stable. The other one flip back and forth, which is kind of cool. Okay, should I plot something? No. I can plot. What did I plot down here? Okay, that's actually pretty cool. So this is I did plot it already. So this is the total Z component of the angular momentum. I think this is Z component. And then this is the angular momentum vectors of the other three. Let's see what I plotted. I'm excited. This is kind of cool. I'm going to write this up as a blog post too. I am plotting T mass A of the positions. Okay, so I didn't calculate the angular momentum. The angular momentum of the total should be constant. I could indeed do that. You could do that as R cross P, or you could do that as I omega. And I could calculate the moment of inertia tensor. But that's in another program. I think I've kind of proved my point that you can model this without using the moment of inertia tensor. So I think it's a win for me. So I'm going to stop right there. Now, I do want to do maybe one more program. I want to make an object with a bunch of masses, more than 3, and at least calculate the moment of inertia tensor and the principal moments of inertia, the principal axis of inertia. But I'm not going to rotate that one because if I want to have, let's say, 100 masses connected by springs, it's going to get really messy, and I don't know if I want to do that. I might do it, but I don't know. Okay, so I'll put a link to the other moment of inertia moment of inertia tensor stuff down below, angular momentum stuff down below, the link to this code down below. So there you go, the end. I'll talk to you later.